everyone, I'm Dr. Rizwana working as a Professor of Physics in Institute of Aeronautical Engineering. So, in my previous video, I have discussed about how laser beam is completely different from normal light source. And also we have taken certain phenomena related to laser emission like absorption, spontaneous emission and stimulated emission. In this video, we are going to discuss further there are some very important terms which we should get familiar in order to understand working of any type of laser system. So here, as you can see on the screen, we have some terms like metastable state, population inversion and lasing action. So if we know about all these terms, then we can go for any type of laser system and it will be easy for us to understand how a particular laser will work. So now moving further, first we are going to discuss about metastable state. As we have seen that in phenomena like absorption, spontaneous emission and stimulated emission. So if you go for absorption, in absorption when we supply external energy, then we have our electron or atom going from lower state to higher state. And this is nothing but excitation of atom from lower state to higher state. Whereas when we go for emission, spontaneous emission or stimulated emission. In this case, we are talking about de-excitation of an atom from higher state to lower state. So here, it means that when we have atoms in the excited state, they may stay in that excited state till their lifetime, or we can make those atoms come down after their, before their lifetime by supplying energy. Now, what you will observe here is this lifetime of particular energy state, it is going to play a very important role, particularly in laser emission. So, as I told you, what exactly is lifetime of an energy state? As we know that in a particular matter system, there will be different energy states. And if we talk about this ground state energy state, we say that its lifetime is very, very large. Actually, we say that its lifetime is unlimited. So, it means that under normal condition, when we are not supplying any external energy, all the atoms, they will be in the ground state forever. Okay, and when we supply energy, then you will observe that whichever atoms or whatever atoms are present in the ground state, they will get excited to different states, higher states, different higher states. And if you take a system, it may consist of different excited state, and these excited state, they are going to have different lifetimes. So suppose here I have taken my ground state and I am naming it as E1, and I have taken here a 3 energy level system. What is 3 energy level system? Where we are talking about 3 active energy levels. So first active energy level is our ground state. Then after that I have 2 excited states and I am calling them as E2 and E3. So these are the 2 excited states. This one is the ground state. Now what you will observe here is of all the excited states that are present in a system, there will be one excited state which has got long lifetime. So here I am not talking about ground state, I am leaving ground state. But why? Because we know that ground state lifetime is very large if you don't supply any energy. But coming to excited states, here we have taken E2 and E3. What you will observe here is out of these 2 excited states, when you compare their lifetime, you'll find that one excited state it is going to have its lifetime more compared to another excited state. Suppose in this case, let us say that this excited state E2, it has got more lifetime. Then in that case, I'll call this excited state to be metastable state. So what is our metastable state? Metastable state is the excited state which has got a long lifetime. And if you look at the figure which is given in our slide, as you can see, this is our ground state and here we have 2 excited state. As you can see, this higher excited state, its lifetime is 10 to the power of minus 7 seconds. And whereas I have one more excited state whose lifetime is 10 to the power of minus 3 seconds. So in this case, which has got long lifetime, I think this value is larger compared to this value. So 10 to the power of minus 3 is larger compared to 10 to the power of minus 7. So here you'll observe that this particular state is nothing but our metastable state. It means that its lifetime is very large. What do you mean by having large lifetime? It means that it is going to retain atom in its state for more time compared to excited state. So once any atom or electron goes to metastable state, then easily it cannot come down. Okay, it will take more time to get de-excited to ground state. And this metastable state, it is going to play a very important role for laser emission. So next, when we go for further discussion, we are going to understand what is the important role played by this metastable state. Then moving further, okay, and of course, when we talk about this metastable state, we can make use of our Heisenberg's uncertainty principle. Now, we may say that why this metastable state, which has got long lifetime, why it is going to retain atoms for more time. It has something to do with width of the excited state. So we know that coming to Heisenberg's uncertainty principle, and if we take statement of Heisenberg's uncertainty principle, according to that statement, it is impossible to specify precisely and spontaneously values of both members of particular pairs of variables that describe an atomic system. So we know we have different pairs. Already we are familiar with a pair where we take delta x and we take delta p, and this has to be greater than or equal to this value h by 4 pi. What is delta x? Delta x is our position, and here delta p talks about momentum. So here we have position and we have momentum, and when we take this particular pair, this value, it should be greater than or equal to h by 4 pi. And here, as you can see, I have taken one more pair of physical variable that will describe this particular principle. And in this case, I am taking delta E and delta T. What exactly are delta E and delta T? Here, if you see, delta T, it represents lifetime of a particular energy level or lifetime of electrons or atoms that are present in that energy level. And what about the delta E? Delta E is energy level width of a particular energy level. Okay, and if I take this particular relation that comes from this uncertainty principle, we'll find that lifetime, it is inversely proportional to width of an energy level. And we know that our metastable state, it has got long lifetime. So delta T value is very, very large. So obviously, what about its energy level width? It will be very small. So it means that long lifetime of metastable state, it is because of its narrow energy level width. So what makes a metastable state to make its atoms stay for more time? Because of its small energy level width. So next, going further, now here we have first, as when I started with my first slide, there I have given three main topics. One is, of course, our metastable state, and second topic is population inversion. So before understanding what exactly is this population inversion, first we should know what do we mean by population related to a particular energy level or energy state. Suppose if I have two energy states, again if I take ground state E2 and if I take, ground state E1 and if I take higher state E2, what you will observe here is they are going to differ in their population. So what is the population? It means that how many number of atoms or electrons are present per unit volume of an energy level defines population of that energy level. And usually what is the notation used in order to define population? It is given by this number n. So n is used in order to denote population, and how many atoms or electrons are present per unit volume defines population of a particular energy state. Suppose if I take ground state E1, I'll denote its population by N1, or it can also be denoted by N0, and then have my another energy state E2. If you want, we can define its population by N1, and you will observe that N0 will be completely different from N1. And generally, if you want to know what is the population of energy state, one formula is given, and that is given by Boltzmann distribution law. And according to Boltzmann distribution law, population, it is given by this particular expression, very important expression that is going to define population of a particular energy state. What is N? N represents population of an energy state E. So if you look at this expression, what is our N? N is population related to energy state E. And how it is given? It is given as N0 exponential minus E by KT. What is N0? N0 is population of ground state. And of course, here K in the denominator, it represents Boltzmann constant. And what is T here? T is temperature. It means that population of an energy state, it is going to change with the temperature. So temperature also plays very important role. And here, generally what you will observe here is, generally if you take ground state, its population will be more. And when we keep on increasing energy state, when we go for higher state, so as energy state increases, what happens to population? It is going to decrease exponentially. That we can make out from this expression. How N and E are related? Here we have exponential minus E by kT. It means that population, it is inversely proportional to energy. So if energy or energy states are increasing, obviously what happens to population? Population will decrease, and how it is going to decrease? It is going to decrease exponentially. Suppose if I take 3 states, here if I try to plot energy level versus population. So if I take energy here, suppose I have taken ground state whose energy is even, right? And then I have taken excited state whose energy it is given by E2. And then I'll take one more energy higher excited state which is represented by E3. And let us suppose that population of E1 is N1 and population of E2 is N2 and population of E3 is N3. And what you will observe here is, when energy level increases, population is going to decrease exponentially. So as you can see, population is decreasing where we have maximum population at the ground state. So this is about the population. Now we are going to discuss very important term, population inversion. So what do you mean by population inversion? So we know that generally, as we were talking about 2 active energy levels, one is ground state, another one is excited state. And if I call ground state energy the population as N1, and if I take population of higher state as N2, and generally we'll observe that population of ground state will be greater than population of higher state. Or we can generalize and we can say that population of lower state will be greater than population of higher state under normal condition. So what do you mean by normal condition? When you are not supplying any external energy. This is what we are showing in this figure. So as you can make out, population of this ground state is more compared to population of higher state. When we are not supplying any external energy, that is nothing but when we are talking about normal condition. But when we go for like a supply of energy, when you are supplying energy, when you are supplying external energy, then what happens to those atoms which are in the ground state? They'll absorb that energy and they'll get excited to higher state. So now if you look at this second figure, in this figure, you can make out that once we supply energy, all those atoms, now here absorption phenomena takes place, where atoms, they'll absorb energy and then they'll go to or they'll get excited to higher state. So here you will observe that at this particular condition, population of this higher state is going to become more than population of lower state. So if this, as I told you, ground state population, we'll take it as N1 and higher state population if we take it as N2. Now in this case, when we have supplied energy, we'll observe that N2 has become greater than N1. Okay, and this particular stage where we are making population of higher state more than population of lower state is nothing but population inversion. Okay, so we can make out from the term inversion, inverting, and there is like another term in order to define population inversion. It is also called as inverted population. So what is inverted population? Generally, we have population of lower state more than population of higher state. But if we are able to make population of higher state more than lower state, in such condition it is called as population inversion. Now, when it is possible to get this stage of population inversion? Now we are saying that after absorption, atoms, they'll absorb energy and they'll go to higher state. Suppose if this higher state lifetime is very, very small, then what you will observe here is within few milliseconds, these atoms which are there in the excited state, they'll come down easily. But we should try to hold this atom for more time in excited state in order to maintain this condition of population inversion. So for that, our excited state, it should have long lifetime. It means that we know that which excited state is going to have long lifetime, which is nothing but our metastable state. So, metastable state, because it has this property of long lifetime, it has its property of holding its atom in its state for more time. So, you'll observe that population inversion always, it will be achieved in metastable state. Why in metastable state? Because its lifetime is more. It will hold atom for more time. That will make population of higher state more than lower state. So we have to understand that metastable state is only make more number of atoms. So that's why our population inversion on having more number of atoms in excited state, it is possible only in metastable state. And thus we can understand more in detail using this 3 energy level system. As you can see in this particular figure, I have taken a system, matter system, in which there are 3 active energy levels. Here I have taken population versus energy. And here what are those 3 active energy levels? We are taking them as E1, E2 and E3. And here E1, we are saying that let it be ground state. So E1 I am calling it as ground state. And what is our E2? E2 is our first excited state. So this is our first excited state, and I am saying that it is in metastable state. Right? And then I have one more excited state, E3, and this we are calling it as higher excited state, and its lifetime is very, very less. So it has got very less lifetime. Okay, so we have taken a system in which we have one ground state and we have 2 excited state. Of those 2 excited state, we are saying that E2 is metastable state, which has got long lifetime compared to higher state. And as I am taking normal condition where we are not supplying any external energy, then if you look at their populations, what is N1? N1 is population of ground state. N2 is first excited state. N3 is second excited state. So you'll observe that under normal condition, N1 will be greater than N2 as well as N3. So here N1 will be greater than N2, greater than N3 under normal condition where energies are E1 less than E2 less than E3. It means that energy of E3 is more compared to E2 and E1. So this is the situation when we are taking normal condition or when we are not supplying any external energy. Now once I supply external energy, first where are our atoms? They are in the ground state. More number of atoms, they are in the ground state. Now once I started supplying energy, suppose I am supplying energy in the form of photons, then what happens to these atoms which are in the ground state? They'll absorb that energy and they'll get excited to E2. Okay, and some will also get excited to E3. So we have atoms getting excited from E1 to E2, also from E1 to E3. Okay, so there are some atoms in E1, E2 as well as there are some atoms from in E3. When these atoms, they are coming from E1 once we supply external energy. And we have seen that comparing E2 and E3, E3 lifetime is very, very less. So within short time, what happens to atoms which are in E3? They will lose their energy, and here spontaneous emission takes place. So within very short time, now atoms which are present in excited state E3, they'll get de-excited to E2 and some may come to E1 back. Okay, but atoms which are there in E2, they have very less chance of getting de-excited fast. Why? Because its lifetime is more. So atoms, they'll try to stay for more time in E2. Now, we have some atoms going from E1 to E2. Also, some more atoms they have added from E3 to E2. And this E2, it will hold its atom for more time. So, what you will observe here is a stage will reach where population of E2 is going to become more than population of ground state. That is nothing but N2 is becoming greater than N1. And this particular condition, it is called as population inversion, where we have made a population of higher state more than ground state. And as I told you, always population inversion, it will be achieved in metastable state only. And why in metastable state? Because it will retain atoms for more lifetime. So moving further, now we'll talk about one more process which is involved in laser emission, pumping. So we know that in order to achieve this condition of population inversion, we need to supply energy. So generally, we know that under normal condition, when we are not supplying any energy, population of ground state, it will be greater than higher state. So even population will be like if I take population of E1 as N1 and population of E2 as N2, then N1 will be greater than N2, and this is the case under normal condition when we are not supplying any energy. Suppose I started supplying energy to atoms which are there in the ground state. Then what will happen? These atoms, they will go up, okay, they'll get excited, and then if they go to metastable state, then they won't come down fast. So what you'll observe here is population in metastable state will become more than ground state. So population inversion is achieved. So we cannot achieve this condition of population inversion under normal condition when we are not supplying any external energy. So this process of population inversion, it will be achieved only if we supply suitable form of energy. So that process of supplying suitable form of energy to a system or to a medium in order to achieve the state of population inversion is nothing but pumping. Pumping means where you are exciting atoms from ground state to metastable state in order to achieve population inversion. Now what we'll observe here is depending upon what type of medium you are taking or what type of matter system we are taking, there are different pumping methods. So different forms of energy can be used for excitation. So here I try to discuss some of the generally used pumping methods. Now if you look at this first pumping method, this pumping method, it is called as optical pumping. And this type of pumping, it is used mostly in solid state laser, and we can take one particular solid state laser like ruby laser. And what exactly is optical pumping? So we can make out from the term optical, it means that we are supplying energy in the form of light or we are supplying energy in the form of photons. So for that, what I am going to use in ruby laser, I am going to make use of xenon flash lamp. So we have helical tube which is wound around this particular ruby rod, and that helical tube, it is filled with xenon gas, and this helical tube, it is connected to a power source. Once we switch on power source, then you'll observe that this helical xenon flash tube, it will give us flashes of light. And each flash, it is going to give us several thousand joules of energy, and this energy, it is used for pumping process. So if we supply energy in the form of light to atoms in the ground state to achieve population inversion, then such type of pumping, it is called as optical pumping. So now coming to second pumping method. As you can see, the second pumping method, it is called as electric discharge or excitation by electrons. So what is electric discharge? So in electric discharge, and usually this method, it is used when we are taking gas lasers, when we are choosing our medium to be a gas. So here what we'll observe here is, we have our tube. So this is called as discharge tube. Generally we'll make use of coarse discharge tube, and this discharge tube, it is going to have electrodes. And of course, one will be your positive electrode and other one will be negative electrode. Okay. And what you will observe here is, and these electrodes, they are connected to a power source. Once we supply power source, then what you will observe here is, you will have emission of highly accelerated electrons from negative electrode. So you have injection of these electrons, highly accelerated electrons in this discharge tube. And here you have your discharge tube filled with a gas. Here you will have gas molecules. So in the tube, we have gas molecules, and in that gas which is filled in that tube, what we are doing, we are injecting accelerated electrons which are coming from negative electrode. And these electrons, because they are strongly attracted towards the positive electrode, they'll start moving with very high velocity. And during their movement, when they are moving with high velocity, they'll collide with gas atoms. Okay, generally we'll make use of stable gases for laser emission. So it can be neon gas or it can be any other gas, but we mostly will make use of these stable gases, and this highly accelerated electrons during their attraction towards the positive electrode, they are going to collide with those gas molecules, and they'll lead to excitation of these gas molecules to higher state. So first, these gas atoms or molecules, they'll be in ground state, and this ground state gas atoms, they are going to collide with those highly accelerated electrons, and they'll gain energy from those electrons, and they'll move to their excited state. So this is another way of sending atoms from lower state to higher state. So here we are taking help of highly accelerated electrons, which will come because of electric discharge. Then next, we have our direct conversion. So here we are making use of our electrical energy directly in order to achieve state of population inversion. Then here we have one more method, and this method we are going to use in helium neon laser. So this laser also I'm going to discuss in my next videos, coming videos. So here you can see in helium neon laser, what we are going to do in helium neon laser. First, I'll fill my quartz discharge tube with mixture of helium and neon gas. Or to be more, like if you want to talk about different types of lasers, I can say that I'm filling this tube with X type of gas atoms and also Y types of gas atoms. So here I have taken mixture of two stable gases. So one is X, another one is Y. And I've told you that electric discharge process. So what is electric discharge? We have two electrodes which are connected to a power source, and when we switch on this power source, then from negative electrode we have emission of highly accelerated electrons. Now suppose these highly accelerated electrons, during their movement inside the tube, they are going to collide with X atoms as well as Y atoms. Then you'll observe that Y atoms won't get affected, but these X atoms, so what they'll do, these X atoms, they get excited from lower state to higher state. This is our electric discharge. Now these excited X atoms, what they are going to do, they are going to collide with the Y atoms which are there in the ground state. Now here collision is taking place between X atoms and Y atoms. Now this X atoms, they are going to give their complete energy to Y atoms. Now these Y atoms will go to higher state. So you are exciting atoms by collision with another excited atoms. So this phenomena, it is called as atom-atom collision. Then moving further, of course, there is one more method, thermal pumping. In thermal pumping, heat, in this case either like heating, okay, or raising temperature, it will act as a pump source. So thermal pumping, it is just like our optical pumping or electric discharge method, where heat, it is used in order to raise atoms or electrons from lower state to higher state. Then we have our chemical reactions. So for that, I have, in order to understand this phenomenon of pumping called chemical reactions, I have taken one example where hydrogen molecule, it is reacting with fluorine molecules. So here chemical reaction is taking place between hydrogen and fluorine molecules, and when this hydrogen and chlorine molecules, when they get chemically combined, when bonding takes place between hydrogen and fluorine, when chemical reaction takes place between these two molecules, then obviously we have formation of hydrogen fluoride molecules. And once we get this hydrogen fluoride molecules, they are already in the excited state. So during chemical reaction itself, whatever product we are getting, that product, it will be in excited state. And what you will observe here is number of produced excited atoms or molecules. Whatever hydrogen fluoride molecules we are getting, they will be more in number compared to normal state atoms or molecules. So if I take ordinary hydrogen fluoride molecules, then they won't be in excited state. But hydrogen fluoride molecules which are created because of chemical reaction between hydrogen and fluorine molecules, they will be more excited compared to normal hydrogen fluoride molecules. So like this also we are able to achieve population inversion. So this is one more method of achieving population inversion. So here we have discussed different process of pumping. So like how we started with metastable state. We have taken metastable state. Then in metastable state, we have seen that there will be one excited state which has got long lifetime. And then we said that we should have this condition of population inversion, where we have to make population of higher state more than ground state. right? So for, and also we said that it is possible only in metastable state. Now next step is sending those atoms to higher state. That is done by pumping. So this phenomena of pumping. Now there is now we are going to discuss very important phenomena, like we have seen when we have taken full form of laser. What is full form of laser? We said that light amplification by stimulated emission of radiation. So we have discussed about stimulated emission. Now we are going to see here in lasing action how our light is going to get amplified. Now this is the beautiful picture which will show us how light is getting amplified. What do you mean by light getting amplified? It is nothing but where we are increasing number of photons. So number of photons, emission of number of photons will be more, and during which process here completely we are talking about stimulated emission. So here we are talking about stimulated emission. Because of stimulated emission, we are increasing the number of photons emitted. So how we are going to increase? So for that, if you look at this figure, now before going to this figure, I'm going to draw a simple figure in order to show stimulated emission. Again, I have taken two states, E1 and E2. Okay, after absorption, where are our atoms? Our atoms, they are in excited state. So we have achieved population inversion. Here, let us suppose that E2s are metastable state. So we are able to achieve population inversion in E2. Now next step is, I have to make these excited atoms come down to E1 before their lifetime. Here I am talking about stimulated emission. I have to force these atoms to come down. So here, first what I'll do, I'll supply one photon. When I supply one photon or stimulus photon, when this photon goes and collides with this atom in the excited state, now what will happen to this atom? It will get excited to E1, and we know that per emission, because of stimulated emission, how many photons are emitted? 2 photons are emitted. Now again, these 2 photons, what they'll do? Now again, they'll act as stimulus energy, and they'll go and collide with 2 more excited atoms which are present in E2, and they'll make these 2 excited atoms come down because of stimulated emission. And then how many photons are emitted? So here I have 2 photons and here I have 2 more photons. So total 4 photons are emitted. Now what these 4 photons are going to do? They'll go and collide with 4 more excited atoms in metastable state. So when they go and collide, they'll make these 4 atoms come down. And again here we have emission of 8 photons. So like this chain reaction will start. We need just one photon in order to start this avalanche or chain reaction where multiplication of photons takes place because of stimulated emission. Same thing we are trying to show in this figure. As you can see here, I have one photon and this is my atom, excited atom in metastable state. So when this photon goes and collides with this excited atom, so because of stimulated emission, it will lose its energy, and that energy it will give rise to 2 photons. Again, these 2 photons, they will collide with 2 more atoms which are there in the excited state. So here, because of one emission, how many photons? Again here 2 photons and here 2 photons. So first have this photon, it has given to 2 photons, and these 2 photons they have given to 4 photons, and then each photon again it goes and collides with excited atoms. So per emission, how many? 2 photons. So like this, as you can see, photon number has increased and it has gone to 8. So this process it is going to continue, and we know that photons which are emitted due to stimulated emission, they are having this characteristic of moving in single direction. It means that they are directional, and they'll be in phase with each other. It means that they are coherent, and they are going to have same wavelength, they are monochromatic, and as we know that there is a lot of multiplication of photons, many photons are emitted, so they are highly intense. It means that ultimately what type of light we are going to get? We are going to get our laser, right? So this is the phenomena of amplifying light. Amplifying light means where we are increasing number of photons by the phenomena of stimulated emission that will give rise to laser. So this is the basic principle behind laser emission, and this basic principle it is called as lasing action. So this is about the lasing action. Now, so if as we know that we have discussed different topics related to laser emission. So that will help us to understand working of any type of laser system. We have discussed about metastable state, and then we have discussed about population inversion, then different pumping phenomena, and then finally amplifying light by stimulated emission. So with this, I'm going to end my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.